All right, perfect. Thanks very much for giving me this opportunity to speak today. I don't think the microphone, okay, it's working. So I'm going to change the gears a little bit. This is not going to be a finite element oriented talk, but it's more of a broad quality processes for bridge analysis models as it comes to verification and validation. So let's get started. When you analyze a bridge, we have a number of options to use, which might be one-dimensional line girdle analysis. It could be two-dimensional line elements, linear elastic finite elements, strata and tie analysis, nonlinear finite elements. So the objectives of this study is to identify State Department of Transportation practices for quality processes of bridge structural analysis models. Bridges are a major or an important aspect of structural analysis in the United States as well as worldwide. So this is more of trying to understand what practices DOTs follow. So what we are looking for, how do they choose appropriately qualified engineers for the modeling work? How do they choose appropriate analysis methods, software? How do they validate the software? How do they model a bridge structure with proper assumptions, approaches, as well as how do they verify the results? More than often, you end up with discrepancies, and how do you reconcile discrepancies between independent models? So these are the aspects that we are looking nationally in the United States to understand how DOT is doing these in the context of bridge structural analysis models. So methodology is literature review, online survey of 51 DOTs, 50 state plus Washington, D.C. DOT, and what I'm going to be presenting involves 100% participation, so it really reflects the national results. Follow-up interviews with 5 selected DOTs we also conducted. So if you look at the big picture, we need to have a quality system, and quality control is a really small aspect of it, right? Quality assurance involves quality control. So this is, the system should be deliberate and it should be systematic to work. And it's really important that upper management should have the support for the system, including documentation, as well as an efficient QA/QC program established. Very important to have established, experienced staff and good relationships between disciplines to put things into a good quality management system. So verification and validation are very important for bridge or any structural analysis models in terms of quality processes. These are used interchangeably, but they are different wording. Verification is not the same as validation. Verification deals with mathematics, but validation deals with physics. So these are two separate concepts. Verification is also described as solving the equation right, but validation is described as solving the right equation. In terms of verification, what we have seen in the previous discussions, for example, sanity check is a verification process, right? It is determining the mathematical accuracy of the solution. So you are checking the mathematics, whether you get it right or not. You can compare your solution with other mathematical solutions. It could be an independent model created by someone else. It could be a different model. Let's say you have a finite element, but you can verify that using a certain time model. You can verify it with hand calculations. You can verify it with some spreadsheet. So you are verifying it mathematically using a different method or different approaches. That could be, sanity checks, independent calculations, line-by-line checking, refined analysis. So pretty much all activities that we do involves verification, right?
They're having a little more fun than this.
All right, is it not? Is it coming from the speaker? I'm guessing it's not. All right, so. So in verification, the relationship of the simulation to the real world is not the question, right? So it's not the issue. But in validation, what we are looking for is the relationship with the real world. Are we representing the physical behavior expected from that system, right? So we are looking for physical experiments to conduct validation study. So you need experimental data. That's the number one requirement for validation. And you are looking how the system represents the real world, right? Other type of activities, sensitivity analysis. So what's the sensitivity analysis? So you are changing some model parameters to see how they influence the global results. So you can do this by understanding, uncertainty, etc. So it's really useful. The other one is calibration, which should be really used with large caution, because this is involving explicit fine-tuning or updating the model to match the agreement with the experiments or with some other validated results, right? So this determines model's fitting ability, but you might also be superimposing errors. You make more mistakes, but you get the right result, right? So this might happen. You would discover this is the case once you model some other structure. You see that, yes, you are getting very good result. You calibrated in to a specific type of model, but if you model something similar, the same category, but a different system, you realize it's completely off because you superimposed errors to get good results in one application, but really bad results in other applications. So calibration should be really used with a lot of caution. So now I'm going to switch to the United States practice in terms of bridge modeling. So I'm going to be, first of all, introducing what quantity of bridge design conducted in each state or nationally, what quality processes are implemented for consultants as well as in-house. So a state DOT might do the analysis themselves in-house. That would be, the third part of the presentation, this one, or they might give it to a consultant to conduct. So let's look at the total number of engineers working for state DOTs. This involves 51 DOTs, completely national results. You can see it's all over the place, but 20 to 40 engineers represent a general, the most represented numbers. You can see how many new bridge design undertaken by each DOT. You can see again 20 to 40 new bridges designed by each state every year, generally. Here what's important is national percentage. So in terms of new bridges, almost 60% designed by consultants. So DOTs are contracting out 60%, they only do 40% themselves. But in terms of load rating, in terms of existing bridges, DOTs are doing more, almost half or maybe a bit more than half, 53% done in-house versus 47% consultants nationally. So the second part of my presentation will look at each state, what type of quality processes are applied to consultants, because such a large number of bridges given out to consultants. So we asked 3 questions. How do you pick appropriately qualified consultants? How do you check models developed by consultants, and how do you verify the results obtained from consultants? So you can see we are asking whether DOTs have processes. So you can see pretty good numbers. Almost 60% has some written processes for choosing consultants. So you can see written processes represented by blue. The minimum number is verifying analysis results obtained from consultants. So you can see 33%, 1/3 of state DOTs have no written process for any of these three questions, right? So they say 0, and about 15% have written processes for all three aspects for consultant-assigned bridge design projects. So these are more, details. You can look at the report. I don't want to take up too much of your time, but what they are looking for: minimum years of design experience, how many similar projects they have done before, how many engineers they are going to be giving it to the project, do they have structural engineering credentials. So you can see the DOT percentages. I think the most represented is minimum number of similar project experience that they are looking based on the results. Approved software in terms of bridge modeling, you can see 39% of state DOTs have some pre-approved software list. They expect consultants to pick from the list. As a consultant, if you want to use something else, there's a bit of a heavy paperwork you need to go through to justify why you're suggesting something else. But 61%, they don't have any approved software. You can use any software you like as a consultant. Do they track what method consultant uses? Generally not. As you can see from the results, the ones which track, which is 15 DOTs, so 15 out of 51 track what method consultant uses. You can see finite element is, nonlinear finite element is really represented with low percentages. Linear elastic finite element is also not very commonly used, but the most common is one-dimensional line girder analysis, two-dimensional analysis. So these are the most often used type, but finite elements are a little bit less used by consultants. So final part of my presentation will look at in-house. So these are the bridges analyzed, designed in-house by state DOTs, and we asked 6 questions. We are asking, how do you choose internally what engineer is going to model the bridge? How do you choose the software? What processes, what documents do you have for modeling guidelines? What processes do you have for validation of the software? What processes you have for verification, and what processes for reconciling differences. So if you look at the results, I'm going to get pointer from here. Let's see. All right. All right. So if you look at the percentages, in-house percentages are definitely much less than consultant processes. So it looks like DOTs have better quality processes for external consultants than in-house design or analysis. So if you look at total number of processes, you will see almost 45%, almost half of the DOTs have 0 written processes for all 6 questions. And only about 7-8% have written processes for 5 of these, and not a single DOT have written processes for all 6. So this shows there is definitely a need for more research and development in terms of quality processes of bridge analysis models. You can see, the analysis methods in-house. Definitely line girder analysis represented by the most used. The least used nonlinear finite element. Linear elastic finite element is also used very rarely. So we can see line girder as well as strut and tie used in-house by DOTs. If you look at in-house versus consultant analyses, it looks like consultants using a little bit more finite elements. As you can see, nonlinear finite element in-house versus consultant, linear elastic in-house versus consultant. So it looks like consultants are using slightly more refined type of analysis. Validation, we can see, how they validate in-house. The most commonly used method is analysis engineer decides how to validate. So that's really putting the burden on the engineer. You can also see data from bridge inspection records. They are using it. This is pretty good modeling of benchmark structure specimens. Some of them are using this method of validation. So this is verification. The most common method of verification is checking of the input parameters of the software. Again, analysis engineer decides how to verify. Another team uses a different method or software that's sort of like a sanity check or independent calculations. So you can see all percentages in this slide. These are about reconciling discrepancies. Let's say you have two conflicting results coming from two teams or within the same team. So you can see the team works to resolve the discrepancies, more conservative sets of results used. Analysis engineer decides how to reconcile. So these are the processes. So case studies, we looked at 5 selected case studies, one from each geographical region: California, Colorado, Iowa, from Midwest, Louisiana, from South, and from Northeast New York, DOT. So, we looked at their processes. These are presented as good examples. For example, California Department of Transportation have a specialized branch on structural modeling analysis only. New York State DOT also has the modeling design branch with 65 design steps. So these are more of a specialized type of groups. They have training documents. They have Bridge Design Academy. They introduce different type of analyses, tools, etc. So you can find these from the project report, which I'm going to give you the link. It's a public document. It's published, so you can download it. A couple of conclusions here, which I already mentioned. The first one, written processes for consultant procedures are better than written processes for in-house procedures. One-dimensional line grid analysis used most often. So what we are recommending as a result of this research is to develop guidance on what constitutes an effective QA/QC process, because there needs to be some national definition of structural QA/QC process that can be followed by engineers. Specific guidance is needed. This is what we heard a lot from engineers. Some examples of finite element models, some examples of certain time models, because it's all about gradual refinement that needs to be done. That also involves creating a model sharing platform nationally. You upload your for example, box beam model, and some other engineer can take it, learn from it, advance it. It's an iterative process. Qualified training system, I think we also recommended this one because at the basic undergraduate level, none of these topics are covered. We are not covering finite elements, we are not covering concrete modeling, etc. So there needs to be some definition of who qualifies to do those type of analysis. There needs to be some certification, some credential to justify that the engineer is really qualified to do that type of a concrete reinforcement modeling based on different load conditions. And again, related to this one, training courses. We need more training courses on modeling. We need to share the expertise. We need to educate junior engineers on how to effectively verify, validate, quality control their work, as well as learn how to use advanced modeling tools. So this is the project report. It's published by NCHRP. Synthesis 620, so you can just download it from this link. It's not too big, but you can get all the graphics, all the data from this document. So I thank you very much for your attention, and if you have any questions, I would be happy to answer.
So is what you're asking or maybe hinting at is maybe more so like developing a standard method for QA, QC that can be used across all 50 states and DC? And if so, how would you do that based on like regions where maybe you have high seismic versus areas where not? I mean, I'm just curious of how easy would that be to do across all 50 states, if that's what you're getting at.
Yeah, that's an excellent question. If you look at the report, we also categorize states based on seismicity. So we have high seismicity states versus low seismicity. So I didn't mention it, but it's in the report. This has been done before, not for quality processes. For example, H2 LRFT, bridge design specification. So they set up some global standards, but each state would be free to choose whatever is applicable to them. So you create like a master document, right? There are different requirements, but you define what is a quality process, because when we go and interview engineers, we realize they are not really thinking about what's verification, what's validation. So those basic definitions should be defined. Some common methods of doing these, as other colleagues presented, should be defined, plus some more specific details that each state can create. For example, each state has a bridge design manual, and they create it depending on what they think important to them. So that bridge design manual should have a section for verification, validation of structural analysis models, which is not present as of yet, but that's what we are suggesting.
So I find in my practice, again, dealing with buildings, that the human factor is a major problem. Mm-hmm. And I predict it would be in the case of bridges as well. The human factor, is there a way to include the human factor in a QA/QC research project, perhaps in the future? For example, there are variations in the interpretation of RFPs. Mm-hmm. I know of a case of a bridge repair brought to my attention where different contractors looked at it differently and priced it differently. And whoever got the job would have been wrong. Mm-hmm. And runaway projects, for example, incomplete drawings going out into bid, unknown to the engineer, initially intended only as pricing drawings, taken into bid, and then became the project with incomplete drawings. Again, it's a human factor. It has nothing to do with the technical part, mostly to do with the human part, but has to be addressed because these are real problems in real life.
Absolutely, yeah.
Thank you. Thank you. Dr. Gunnar?